Windowing is one of the less talked about aspects of TCP, but it's very important because it can severely impact network performance. Before we talk about what windowing is, we need to get a clear picture of the problem that it was designed to solve. If a TCP host can't process the packets as fast as the sender is sending them, those packets have to be stored somewhere on the receiving host temporarily. That storage space is called a buffer. If a receiver's buffer gets full and can't store any more packets, those packets will get what is called tail dropped. Tail drops cause reduced throughput and other problems that we'll talk about a little bit later. Right now, let's talk about windowing and how it can actually cause the very problem that it's supposed to solve. The window size is simply the amount of bytes a host will send before it expects an acknowledgement. Suppose that host A and B agree on a window size of 65,535 bytes, which is the maximum window size supported by the TCP headers. This means that host A will send up to 65,535 bytes to host B before it stops sending and waits for an acknowledgement. No problem there, right? Well, suppose that host A and host B have a TCP connection set up across a 10 megabits per second link with a delay of 80 milliseconds. We can use this bandwidth and delay information to figure out how much data host A can send before host B even receives the first byte. This is called the bandwidth delay product. So how much data can host A send to host B before host B receives that first byte? And why do we even need to know that? Well, let's figure out the answer to the first question, and then we'll tackle the why. The bandwidth delay product is simply the bandwidth in bytes per second times the delay in seconds, which will give you the bandwidth delay product in bytes. 10 megabits per second comes to 1,250,000 bytes per second, and the delay is 0.08 seconds. That gives us 100,000 bytes as the bandwidth delay product. This means that host A can theoretically push 100,000 bytes out before the first byte even gets to host B. But the window size is 65,535 bytes. This means that host A is only going to send that number of bytes, and then it will stop because it must wait for host B to send an acknowledgement. This effectively reduces the throughput, which, as you remember, was the very problem windowing was supposed to solve in the first place. What to do? Well, to solve this problem, RFC 1323 defines the TCP window scale option, called window scaling for short. Basically, TCP window scaling sets a TCP option that communicates what is called a shift factor that multiplies the window size. The maximum TCP window size is, as we said, 65,535 bytes, and the maximum shift factor supported by the window scaling is 14. That means that when TCP window scaling is enabled, the maximum effective window size is 2 to the 30 bytes, or about 1 gigabyte. TCP window scaling must be enabled on both hosts in order to use it. If one of those hosts is a Cisco router, the command IP TCP window-size will enable it.